Well, welcome back. This is part 2 of the bouncing ball video, and I was just going to finish up by talking to you about the analysis that I performed on the data. And what I decided to do was to graph my data as a scatter plot to see if there were any trends. So I'm going to show you that in just a second, but the short answer is yes. When I graphed it, I could definitely see a trend, and I was able to use that trend to make predictions. So let me reveal the graph here. And I'll zoom in. And so what you see here is a graph of the bounce height versus the drop height. One thing I want to point out right away is that we, in an experiment, if you graph data, you're always going to put the independent variable on the horizontal axis. So remember, the drop height was the thing I could control. That's my independent variable. And so that always goes on the x-axis. On the other hand, the bounce height, that was my dependent variable. And we always put the dependent variable on the vertical axis. That's just a thing. It's a thing in science and engineering and economics. Usually the independent thing goes down here, the dependent thing goes on the side. When you look at the data, you can see the points. Here they are. They look like they're all kind of falling on a line, which they really seem to be doing. So I had the computer program draw a best fit line to go through the points as best as it could, and it worked pretty well. So that's actually a pretty significant result. Whenever I see something that looks like a line in a graph, I get all excited, and I think that's wonderful because a line is mathematically pretty easy to write an equation for. Okay, so the fact that we have a linear graph, right, a line-shaped graph, means that we have a direct relationship between the two variables. Okay, a direct relationship. And I usually can use some type of a program to figure out the equation of the best fit line. And I hope you guys recognize that formula from math class. So I'm going to get that from the computer program, and the computer program is going to tell me that it's going to give me a slope, which is m, and it's going to give me a y-intercept, which is the b value. Okay. So this is the equation that the computer spit out for the best fit line. Okay. The slope is 0.756. The y-intercept is 3.27. I want to remind you that x was the drop height, right? That's my independent variable. And y was my bounce height. That was my dependent variable. So what's nice about that is that if I want to plug in a bounce height, I can always go back and I can get x. I can solve for the drop height. And that's how I did my prediction. Okay. So there's a lot of words here, but the idea would be that I now have a way of predicting where to drop the ball in order to get it to bounce to a certain height. I tested the accuracy of the equation by trying to predict what height to drop the ball from. So it goes to a height of 85 centimeters, so that was my testing height. And all this stuff is just kind of the math, and what I'm trying to do is I'm trying to solve for x. I'm trying to solve for the drop height if I know that I want it to bounce to 85 centimeters. And so this is just algebra, and then you can solve for it, and you find out that the drop height should be 108.2 centimeters. Should be. And so that was my prediction. So this model that I'm using is I'm using a graph to create a visual model of the data, or a graphical model, and that linear relationship is helping me to then build a mathematical model, right, which I can use to make my prediction. So we're going to be really trying to do a lot of graphing in these investigations, and if possible, trying to fit our graphs with lines whenever we can, because lines are really easy to deal with. There's this cool guy. Yep. And just to kind of put it at the end here, how did things turn out for me? Well, I don't want to be braggadocious, but it turned out I had a 1.1% error on one trial, and I did a second time, and I got a 0.9% error. So that's pretty good. You know, you're talking about a 1% difference. And usually in experiments, like in a physics lab like this, 1% difference is really good. And so we're going to just be happy with that. Usually if you get a percent difference of like more than 10%, you should start asking questions about like whether or not your procedure was good or if there was some type of error that you couldn't control. So there's things you should think about. But if you're getting like a 1 or 2 or 5% error, that's actually not bad at all. Okay, so success and happiness. All right, so these are, I wanted to go through this to kind of give you an idea of, what are the things that make for a good lab. Okay, and I know that you have also a rubric that you can take a look at that's also going to kind of list the different components of what I've just gone through. And what I'd like you guys to do is to try to work and write your own, design your own labs and keep these things in mind. So when you're writing that procedure, be really specific so somebody else could do it. And when you're planning the experiment, make sure you know what the independent variable is. Make sure you know what the dependent is. Tell the person that when you write it up. Okay, so those are things you should look for, and you can look at that rubric that you have to kind of remind you about that stuff. This presentation also is posted on today's classroom post, so if you want to go back and look at it as you do the activity, feel free and kind of use it for some help. Okay, so I'm going to let you guys try this out and practice a little bit with a little activity, and I wish you luck. Bye-bye.